Hi, my name's Kameron Hansen, and I'm going to be talking about tuning excitons in two-dimensional metal halide perovskites. I'm also at the end going to talk about some recent measurements we've done that show that these excitons have partial charge transfer character at room temperature. And I'd really like to thank my collaborators, the PhD advisor, and funding sources, without which none of this work would have been possible. So jumping into it here, the bulk of my PhD research has been applying one technique to one material, that technique being electroabsorption, or the difference in a material's absorption with and without an applied electric field, the material being 2D metal halide perovskites, which probably don't need much introduction here. Now, why EA on 2D perovskites? So this comes down to something I'm going to call gallium arsenide envy, or 3-5 semiconductor quantum well envy. So in these systems, they achieved a high level of agreement between theory and experiment in the electroabsorption signal, led to some high impact studies. And electroabsorption, or EA for short, was the most significant technique to advance our fundamental understanding of the excitons in these systems. And additionally, to precisely measure the exciton's properties. So if we compare that to 2D perovskites, so far EA studies have been few. They've been contradictory in their analysis of the EA spectrum. And this really speaks to the intrinsic complexity of excited states in perovskites. There's simply lattice effects in these materials that don't need to be accounted for in the 3-5 compounds. So in pursuit of understanding 2D perovskite EA signals, my PhD has taken a threefold approach to that. On one hand, I've simulated the EA spectrum of a 2D one-year exciton to better understand where the features originate from. So using the theory of the gallium arsenide quantum wells, but applied to perovskites. Collect EA on multiple chemical compositions to see how the EA features change as you swap lead out for tin or iodide for chloride or so on. And then lastly, considering lattice effects that fall outside this theory. So my collaborator, Dr. John Colton, has been talking about our work on the simulation side. And today I'll be talking about the difference in chemical compositions and the lattice effects as the last part of the presentation. So jumping into the first story, I again want to frame this in the context of 3-5 quantum wells of the past, where it really was advancements in the molecular beam epitaxy, the way that these materials are made, that allowed for fine-tuning the exciton properties and led to their successes in industry as electro-optic modulators, LEDs, lasers, and so on. So these figures are taken from a Nobel Prize winning paper where they made a blue light emitting diode by finely tuning the layer composition and thickness using molecular beam epitaxy. Now, 2D perovskites are not made with molecular beam epitaxy, but instead nature has provided an alternative pathway towards tuning the exciton properties through the wide catalog of molecules and atoms that naturally crystallize into the 2D perovskite structure. We have been applying electroabsorption to obtain precise measurements of the exciton's binding energy and radius and mass and so on. We've been doing this for a range of different chemical compositions. And prior to this, if you go look in the literature, the measurement variance in the exciton binding energy, probably the exciton's most important parameter, is roughly the same order of magnitude as the variance between different chemical compositions. So, establishing how the binding energy changes when you swap lead out for tin or something like that is a fundamentally flawed endeavor under this regime. We first have to reduce the measurement uncertainty. And that, for that, I'll refer you to my collaborator, Dr. John Colton's talk, if you're interested. But for now, it sufficeth to summarize it as just telling you that in the electroabsorption spectrum of these materials, we get a start shift of the exciton that creates a first derivative line shape in our EA spectrum. And then the continuum wave function leaks into the band gap, creating a Franz-Keldysh effect. We simulated this in a recent paper, and you can precisely determine the binding energy by the difference between these zero crossing points. And experimentally, the way we measure this is by spin coating polycrystalline thin films onto an array of electrodes like this. So here's some measurements for different 2D perovskite compounds: phenethylammonium lead iodide, phenethylammonium lead bromide, phenethylammonium lead chloride. And we see that there appears to be a correlation between the band gap energy and exciton binding energy. Now, repeating these measurements for 11 other compounds and putting them all on a plot here where the horizontal axis is band gap energy, vertical axis is exciton binding energy, we see they do follow a trend line where here I have the colors represented by different organic molecules in the barrier layers. So for example, ethanol ammonium down here, which is the outlier, has a much lower binding energy because it has a much higher dielectric constant. So we're tuning the dielectric mismatch in this direction. And then in this direction, it's the polarizability of the inorganic layer that determines where it falls on that trend line. Now here's the trend line. This is the same plot, just zoomed out and plotted in comparison to this theoretical scaling law for 2D semiconductors, where the binding energy is about a quarter of the band gap energy. Now, if we were to somehow exfoliate these layers down to just the metal halide layer and put that in a vacuum, these values would fall on this trend line. It's interesting, and we're planning on using these all of these precise measurements as input parameters in collaboration with some computationalists to, advance our understanding of the dielectric confinement and predict exciton binding energy variance for, n equals 2, n equals 3, and so on, and even three-dimensional perovskites like methylammonium lead iodide. With that, I'm going to just transition into the second part of the talk, the second story, which is the fact that we measure some charge transfer character in these excitons near room temperature. Now, this comes down to an anomalous observation we had, and that's the EA line shape shows a strong temperature dependence. Here I have the EA line shape, the EA signal plotted in red in comparison to the first derivative of the absorption in black, a solid black, and the second derivative of the absorption as a dotted black line. Now, clearly the EA follows the first derivative line shape, but as you move to higher temperatures, it more closely resembles the second derivative. Now, a second derivative component in the EA signal is not expected for a Wannier exciton, and this temperature dependence in the line shape hasn't ever been observed before for a crystalline solid. So we, took a step back, considered all sorts of effects that might be at play here. I'll first talk about the physical origin of these line shapes. So essentially, the exciton peak can shift from the quadratic Stark effect, or it can broaden from the linear Stark effect. And through this, we can measure by doing a linear regression fit with our EA signal and the derivatives of the absorption, we can measure the exciton's polarizability and dipole moment. Now, repeating this for a range of temperatures, I'm just going to draw your attention to the plot on the right side here, where we see we're doing these derivative fits for a range of temperatures, measuring the dipole moment monotonically increase with temperature and the polarizability decrease with temperature. So this large dipole moment at room temperature leads us to conclude that the excitons have some charge transfer nature. And really the physical mechanism at play here is the principle of a dynamic or a disorder-induced dipole moment. So if you have some particle in an asymmetric well, here is just the x-axis projection. We've done a couple of very crude simulations of modeling the exciton's wave function, where you just have the depth of the well determined by the exciton binding energy, and then the asymmetry representing the magnitude of the disorder. And as the phonon modes populate with temperature, they, because the nuclear coordinates are very ionic, that significantly, and they're dynamically active, at room temperature that perturbs the energy landscape of the exciton, introducing some disorder. And, if you just shift one of these barriers smaller in a finite well case, the charge density actually shifts to favor the lower energy side, creating a dipole moment. The model predicts, greater dipole moments at high temperatures, greater dipole moments for compositions with lower exciton binding energy, and greater dipole moments for disordered samples. And we see all of these check out with our experimental measurements. And we are working with computationalists to develop some, actually run these calculations from first principles and calculate the excited electron and hole wave functions under different disorder regimes, and to capture this dipole moment effect. Just to conclude here, so exciton tunability, we've see that substituting in chemicals largely affects the binding energy, and it can be tuned over a wide range. And we plan to do a lot of future work to advance our models of the dielectric confinement. And then finally, this charge transfer nature. The thermal distortions in the ionic lattice create disorder in the exciton's energy landscape and thereby induce a dipole moment and localize the electron and hole wave functions, which reduces their polarizability. So we're also working on studying like static disorder effects. So I thank you all a lot for your attention, and we'll conclude there.